What's up, everybody? Hope you guys are doing well. Cheers. That's some good creamer.
Bobby Yamamoto.
All right, a few different announcements for you guys. Algebra 2, you guys are first. You guys have a quiz this week on section 4-5. It's going to start at 10 a.m. just like usual. Group B will be going at noon. So if you can't make the 10 a.m. quiz time, shoot me an email and I'll get you in the second group. Now, in regards to end of the year stuff, you guys already saw that you won't be having a final, so we'll be doing something different for that. I'll let you know later. But I will still be dropping the 200 points. Yes, still dropping those 200 points. That way it kind of just takes care of any inconsistencies throughout the online learning format. Um, Now for the binder check, I'm not going to be doing the binder check for obvious reasons. I don't see you guys. You guys aren't in class, so there's really no way for me to do it. Um, so that hopefully it kind of balances out the dropping in 200 points, no binder check, and then not having the final. If you guys have any questions about that, let me know in an email, and I'll try and clear things up. But no binder check, yes, dropping those 200 points, and then you guys saw the no final. We'll be doing something different, but I'll let you know later. You guys hear that? In regards to extra credit, I'll be trying to think of a extra credit assignment for both Algebra 2 and Geometry, which I'll do that soon, so you guys can get working on it. Make sure you guys are submitting any late work that you have. I'll try and give you as much partial credit for that 3-day period after the 12th. If you guys have any other questions or want extra help, make sure you let me know in an email. I'll try and answer it there. Or if you want extra help via video conferences, then we can set up a time for that as well. All right, that's it for me. Hope you guys enjoyed the lecture. See ya.
All right, so we're starting a new section, section 4-6, which is looking at the natural base e. So we're learning a new number. So first, let's remember I. Who remembers what I is? And if we're in class, I'd wait for somebody to answer, and hopefully you guys remember that I is equal to the square root of -1. Then I'd ask, who remembers what pi is? Hopefully you guys remember that pi is equal to 3.14, and it goes on forever. It's an infinite number. Now our new number, it's an irrational number just like pi, is e. That is our new number. Now e is equal to 2.7182818, and it keeps going. Just like pi, it's an infinite number, but this is our new number, e. Now, why is e useful? Well, exponential functions with base e have the same properties as functions that we have previously looked at before. So for example, the graph f of x equals ex is like other graphs of exponential functions, such as f of x equals 3 raised to the x. So previously we've looked at functions like this. This is exponential, and we remember that we have all the growth and decay. That's what we looked at previously. Well, our new exponential function with e as the base, so f of x equals e to the x, well, this is the same thing as approximately 2.71 to the x. So just like before, same principles apply. It's still an exponential function, but this letter e, this number e, is a special number. So this is our parent function, e to the x. The domain is all real numbers because this over here is my graph. Notice the exponential function, and it goes left and right forever, so our domain is all real numbers. Now the range, going vertically, notice that there's an asymptote at y equals 0, so anything above y equals 0 works because this graph just gets closer and closer but never actually touches the x-axis. So our range for the parent function is to set a y value such that y is greater than 0. And again, this is our parent function graph. So let's look at how to graph exponential functions by hand, making a table. We're going to treat this just like I would any other exponential function. So here's my graph. Now you might notice that we're adding 2 outside, so you might start thinking vertical shift transformations. But let's do it by hand, and let's start with -3 to +3. That's a good starting point. Well, our first value is if I go e to the -3 plus 2, well, that is going to give me just 2. So my first value here is going to be 2.0. And if you were to enter that into your calculator, then you could, on your calculator, notice that you have your e to the x button right here. Right there, e to the x. So what you could do is hit second ln, that goes e to the x, and you're going to have to enter a value for x, which is going to be -3. Then you'll get your number, which is 0.049787, and I'm going to add 2 to it, so you're going to get 2.04, and if I round to the nearest tenth, that would give you 2.0. Now you could also round to, you could do 2.05, and then you get 2.1 if you wanted to round to that. So it's really depending on what you're going to round to. I'm just going to round to and get the tenth and get 2.0. Now for -2, I'm going to do the same thing, but now I'm going to do e to the -2 plus 2. Well, that's going to give me 2.1, and I'll fill out the rest of these just using the same process. -1 is going to give me 2.4. 0 is going to give me 3. And the reason for that one, just a quick explanation. If you have e to the 0 plus 2, well, anything to the 0 power is 1, so we get 1 plus 2 is 3. And then e to the 1 plus 2 is going to give me 4.7. Then we get 9.4 and 22.1. So those are all the values for x and y, and then you plot them, and you get this function here. Now the domain is all real numbers because it goes left and right forever. The range is going to be y such that, now where is the horizontal asymptote? Notice it's right here. That's where my graph approaches that right there, and that is at 2. Y equals 2. And notice that's a vertical shift upwards by 2 units. So we're going to say that anything above 2 works, so y is greater than 2. But it doesn't equal because it doesn't actually touch the line. So that's how you graph your exponential functions with e. And again, you can use your calculator to graph it as well. Just note that the E button is right there, so you're going to have to hit second and then ln. So example B, go ahead and graph this one on your own. Go ahead and pause the video and try it by yourself. But to get your XY table, and that'd be f of x, you're going to have, so we had -4, -3, -2, -1, 0, 1, 2. That's going to give you -2.982, -2.95, -2.865, -2.632, -2, -2.9, 0.2817, and then 4.3891. So the way I got all those was that I used my calculator, and I went into y equals. After I hit y equals, then I entered second ln. So second ln. That brought me up to I have y equals, and I have e to the, that's what it looks like. And then after I did that, I hit x right there, and then that brought me to this. And then I had to close the parenthesis, so I hit the close parenthesis button, and then I hit minus 3, so I get e to the x minus 3, and then graph. And the function that I get looks like that. Notice that I have my horizontal asymptote right here, which is at y equals -3, which makes sense because it's a vertical translation down 3 units. So the domain, all real numbers. The range is a set of y values such that y is greater than -3, not equal to. So that's how you graph your e functions, exponential functions of base e. But now let's go ahead and look at the natural log. So a natural logarithm with base e is called, or a logarithm with base e is called a natural log. So the way that we abbreviate a natural logarithm is ln, rather than log base e. So instead of writing log of e, just write it as ln. So there's an assumed base of e right there. It's kind of like a common logarithm, but we can write it as a natural log. So the domain of our, if we were to graph this, the domain is x is greater than 0. The range is all real numbers, because the natural log function is the inverse of the natural exponential function e to the x. So the natural log function and the natural exponential function e to the x, they're inverses of each other. So when we look at our graph down here, we see we have e to the x. That's our natural exponential function. Here's our line of reflection, and here's the inverse, which is log of x, the natural log of x. Now, how do we simplify expressions with either e or our natural log ln? We'll start with this one, question A. I have ln of e raised to the -2. Well, remember that ln is really just log base e. So if I could rewrite this as log base e of e to the -2t, well, these cancel each other out, think double b, and I'm left with -2t. That would be my evaluation here. That's what this is equal to. So the trick here is that whenever you see ln and e next to each other, they cancel out and you're left with the exponent. That simple. Same thing here. E and ln are next to each other, so I'm left with that guy right there. And I'm done. So hopefully you guys see how simple these questions can be. And then let's look at question D. Now this one's a little bit tricky because we see that E and ln are not right next to each other because I have the 5. So how do I take care of that? Well, the trick on this is that I'm actually going to reverse plug this. So what that means, I'm going to take that 5 and move it to the exponent. So I'm going to take this 5, move it to the exponent, and that will give me e to the ln of x to the 5th. Now they're next to each other. I'm left with x to the power of 5. And then I'm done. So here's 3 other questions. Hopefully as I write them, you guys are all already solving them. So we're going to solve those. Before I do. Alright, so number 1 solution, those cancel out, 3.2, and you're done. Number 2, I'm going to have to reverse plug this. Get that, those cancel out, I'm left with x squared. The last one, they're next to each other, they cancel out, so I'm left with x plus 4y. And I'm done. And that's it. Now tomorrow we're going to be looking at more complex problems using e and our natural log, ln. We'll do some more economic applications and some word problems, but understand these base concepts because they are useful. Alright, have a good day.